In this video, we are going to look at problem 3698, split array with minimum difference. So we are going to use while loop and partial sum to address this problem. Therefore, the term complexity will be linear and the space complexity will be constant, right? So let me quickly go over the problem statement. So we are given an integer array called nums. So we want to split the array into exactly two subarrays, left and right, such that left is strictly increasing while right is strictly decreasing. So we want to return the minimum possible absolute difference between the sums of the left and the right. If no valid split exists, we are going to return -1. So here, if you look at the three examples, the example 3 is the one which no valid split exists, so the answer is -1. While in the first two examples, the split for the example 1 can be at index 0, right? So from 0 up to index 0, so that's the 1 can be used as the left and the remaining the right, right? Or it can end at index 1, right? So then you compare the absolute difference, you get 2. So in the second example, so you can end at index 1 for the left, or you can end at index 2 for the left. Then you compare the difference, you get 4. So here actually we should observe that. So if there were valid splits, there are at most 2, right? Like in the case of example 2, right? So for some list, it's possible they have an extreme, a largest element. Well, for some others, it might have like something like this, right? Here I'll give you an example. 2 same elements. You have something like say 1, 2, and then 1. So for this, you can have only one split, that is ending at index 1. You cannot end at index 0, right? Because 2 to 2 is not strictly decreasing. You cannot ending at index 2 because 1 to 2 is not strictly increasing, right? With this intuitions, hopefully you have established the intuition. So our algorithm will be the following. So first we try to get the peak point. So basically for loops, right? For loop, so L, as long as, unless I change this nums to be A just for convenience, if AL is less than AL plus 1, for sure we want to make sure L plus 1 is inbound. So we're going to move L to the right. Similarly, R, so at very beginning pointing to the end, if AR is less than AR minus 1, also we need to make sure R minus 1 is inbound. So we're going to shift R to the right. Then we compare L and R, right? So if R minus L is larger than 1, so there's no valid split. So this you can see here. So L will be 0 and R will be just 2. 0 and 2, the gap, so there's no valid split. So here you can check, see example 3. So after this, we will have two cases. One is R equals L. So this is like, say, example 1. So in this case, you have two valid split points, right? For example, in example 1, you can split at 0 and 1, right? So example 2, the left and right are both ending at 2. You also have two valid splits for left. One is at index 1 and the other is at index 2, right? So example 1 or 2, right? So another one is R minus L equals 1. Let me give you an example. So here, 2 and 2, right? So I'll just use this one, right? So this will be L, this will be R. So here L equals 1 and R equals 2. The difference is 1. So, but you can only have one valid split. So here is at index 1. In this example, at index 1. So in other words, in order to get the final result, we need at most 2 comparisons. So with that said, we can address this problem easily, right? So this first part is to locate L and R, right? And then consider relations of L and R, right? So one is this one, and the other is this one, and the third is this one, right? So once you cover these cases, you should be able to get an easy solution to this coding. So now let me write the code. So here first I get the length of this array. So then we point L to be 0, and then shift L to the right. So while L is less than a minus 1, because we want to consider L plus 1, right? And AL is less than AL plus 1 strictly, right? So this way we can push L to the right. Similarly for R, R is initially a minus 1, and well, R is greater than 0, corresponding to this one, because we need to consider R minus 1. And if AR is less than AR minus 1, so we are going to decrement R, right? So up to here, you can print out the L and R to see their relations, right? So you can run it. So for this case, both L and R equals 1. For this case, both equals 2. For this case, L and R's difference is larger than 1. For this case, L equals 0, R equals 1, difference is 1. For this case, difference is also 1. You can only add any and here, right, for the splits. So with that said, let's consider the different cases. So this can be regarded as a big step. Step 1, see a while loop, right? And then we compare, say step 2, compare the relations of L and R. So also we can prepare the return. So once we get the left subarray, and then the right subarray sum will be the total sum minus the left array sum. Therefore, we can, let's first get an edge case, right? So edge cases of if R minus L is greater than 1. So in this case, we just need to return -1, right? And then we can get a total of the sum, and then the partial sum. So we can at least using the split at index L or L minus 1. So in other words, we have a partial sum. We can first have this partial sum to be sum of A ending at index L minus 1, right? So it depends on if L equals R or not. So we consider this 2 cases. If L equals R, right? In this case, we have 2 possibilities. So we can, so this is the ending, the split at L minus 1. We can also split at L, right? So here in this case, so we can have result equals absolute. So the total minus 2 times the partial, right? So this corresponds to as a split at index split at index L minus 1. So if we split at index L, so the result will be min the first result, then the ABS, so the total minus the left side, that will be partial plus A at L, right? Then we just need to return the result. This is the one case. Otherwise, because we have considered this case, so we should have L equals R minus 1. Or if you like, you can do something like this. L if R minus L equals 1. So in this case, you have only one consideration. You just need to split at index L. So you need to return this one. Right. So if you have else, if you like, you just return -1 to catch all the other cases. In principle, you don't need to do this because of this. So now let's do a run. Yeah, it passes all those cases. So now let's look at the generic case. Yeah, it passes all the cases. So here I would say the main point of this problem is to first locate the peak elements. So the peak element can be 1, can be 2, right? And then so then you consider the indices for the peak elements. If there are 2, so you could only have 1 split points, right, like this. If just 1, you have 2 potential valid split points. So in other cases, if they have a gap, so there's no valid split. So the ingredients we use are actually just a while loop and partial sum. And therefore, the term complexity will be is O(n), and the space complexity is O1 actually. So with that said, I guess that's it for the current video. Thank you for watching.